So in the previous video, I went through and reminded you of some stuff that you learned back when we were talking about function transformations, and then showed how we can use that knowledge to come up with the graph of a function like f of x equals 2 times x minus 4 squared minus 2. Unfortunately, I then made the case that that's not the function that we want to graph. The function that we want to graph will be something like f of x equals 2x squared minus 16x plus 30. But using the power of algebra, we were able to show that in fact these are the exact same function, just written in different formats, which kind of provides us with the motivation that we need to learn how to change this format, which we don't currently know how to graph, into this format, which we can graph using what we learned with function transformations. In this video, I want to set the table to show you how we go from this form to this form. Again, the motivation being this form is ungraphable using our current knowledge base, but this form is fairly easy to graph if we understand function transformations. To go from here to here, the process is called completing the square. So how do you complete the square, you might ask? Well, the key to completing the square is expanding binomials. What I mean by that is rewriting something like x plus 3 squared without any parentheses, if you want to think about it that way. It's tempting to think that this is x squared plus 9. You kind of take this square and distribute it into the parentheses, but it actually doesn't work out that way. When you write x plus 3 squared, you want to think about it like it's x plus 3 times x plus 3. And then maybe the acronym FOIL will help you remember that we have to take this x times this x times this 3 times this x, and this 3 times this 3. So what we get is x squared from the first terms in each of the parentheses, x times 3, or 3x, from the outer terms in the parentheses, a 3 times x, or another 3x, from the inner terms in the parentheses, and then a 9, the 3 times 3, for the last terms in the parentheses. We can combine like terms here and make 3x and 3x into 6x, and we end up with x squared plus 6x plus 9. This is probably something you've seen before, but you want to be at the point where you can come up with these answers without writing all these intermediate steps. It would be ideal if you could look at this and immediately knew that this expanded to x squared minus 8x plus 16. And you knew that this expanded to x squared plus 3x plus 9/4. And if you're wondering how I did those so quick, really I'm just taking advantage of the same work that we did up here, but kind of recognizing some patterns. Because these binomials will always come in the form x plus or minus some number, when I expand them all out using FOIL, the x times x will always leave me with an x squared as my first term. The O and the I in FOIL, informally speaking, will always leave me with the product of these two things, so negative 4x in this case. But there'll be two of them, one for the outer terms and one for the inner terms, so the negative 8 coefficient in front of the x term really just comes from 2 times the negative 4 that I see right here. Similarly, if I take 3/2 and multiply that by 2, I get 3, which is what produced the 3 that I see right here. All that leaves is what's referred to as the constant term, the number out here at the end. But where that comes from is whatever number I have here times itself. The L in FOIL, if you want to think about it that way. So just like 3 times 3 gave me this 9, negative 4 times negative 4 gives me this positive 16. Similarly, 3/2 times 3/2, or 3/2 squared, gives me the 9/4 that I see as the constant term right here. And if you recognize those patterns, that the expanded form will always start with an x squared, and then the coefficient on the x term will always be double the number that you see here, and the constant term will always be the square of the number you see here, it's really easy to expand these binomials. In fact, it's so easy that you could even work backwards. If somebody gave you the expanded form, it'd be fairly easy to write it into its factored form. If I started you out with x squared plus 10x plus 25, it'd be awesome if you could come up with x plus 5 squared here. And you're like, yeah, I can do that two different ways. I could say that this 5 squared gave me the 25, and therefore the square root of 25 would give me this 5. And while that's entirely true, you got to be a little bit careful there, because just like a positive 5 squared gives me 25, a negative 5 squared would also give me positive 25. So it's a little bit dangerous to use the number here and take the square root to figure out the number here, because you lose track of the sign, whether things are positive or negative. Maybe a better strategy is to take the coefficient on the x term, the linear term, the positive 10 in this case, and divide that in half to get the positive 5 that you see right here. You'll notice that that purple method of doing things would produce a negative 5 down here, whereas if we tried to do the green method of doing things right here, we might not know whether this is positive 5 or negative 5. Anyways, if we're lucky enough to have the expanded form, coming up with the factored form is really easy. We're only missing one number, and that number is always half of the coefficient on the linear term because the linear term is always double the number that you see right here. So in this case, I have x squared minus 4x plus 4. I take this negative 4 and cut it in half. I get negative 2. So negative 2 is the number that I would write right here. And this even works if you're dealing with uglier numbers like fractions, for example, because half of 9 is 4.5, or 9/2 if you want to write it as a fraction. X squared plus 9x plus 81 over 4. If it's going to factor as x plus something squared, it has to be x plus 9/2 squared. That's it. So far, nothing too bad. If you have the expanded form, you can always come up with the factored form without too much trouble just by cutting numbers in half and recognizing little patterns. Unfortunately, for our purposes, which again is to go from this form to this form, we won't have this entire expanded form. So what you'll have to be able to do is kind of solve a puzzle, for lack of a better phrase. The information that you'll be given is an x squared and a 10x. You won't know what the constant term is here, and what you'll have to figure out is what number goes over on the left side of the equation and what that constant term must be. If you just started the video right here, you might really struggle with that, but if you learn the patterns that we learned up above, it's actually fairly easy. I can cut this positive 10 in half to create the positive 5 that I see right here, and then I can take this positive 5 and square it to get the positive 25 that I see right here. The good news is this is the last level of abstraction. This is as hard as these get, is doing this. The bad news is the natural way you'd figure out these two blanks is by taking this 10, figuring out this blank first and this blank second. However, when we do this completing the square process, as you'll see later in this video, we need to figure out this 25 before we figure out this 5. So ideally, we'd be able to take a puzzle like the one that you see down here and figure out what number goes in this spot first, and then figure out what number goes over in this spot. But that's actually not so bad, because in the same way that this 10 kind of eventually produces this 25, this negative 12 is going to kind of eventually produce the blank that's over here. To get to this 25, we took the 10 and cut it in half and then squared that result. So if I didn't have, I don't know, a blank on the other side of the equation to fill in, I could say that this 10 divided by 2 squared gave me the 25 that I see right here. And using that logic, maybe you'd agree that there should be a 36 over on this side of the equation. Where did that 36 come from? I took this negative 12 and I cut it in half to get negative 6. And then I squared that negative 6, which gave me the positive 36, the number that I'm writing over here. Now that I've figured out this 36, now I'm going to figure out what number goes on this side. And you might argue we've kind of already done that. Half of negative 12 was negative 6, so it should be x minus 6 over on this side of the equation. To make sure that makes sense, let me do two more real quick. If we had x squared plus 5x on the right side of the equation, and we had to figure out this blank first, we take the 5 and cut it in half to get 5/2. And then we'd square 5/2 to get 25/4. Then and only then do we fill in the blank over on the other side of the equation, where we say half of 5 is just 5/2. So x plus 5/2 squared equals x squared plus 5x plus 25/4. One last example. Over here, there's a negative 1 as the coefficient on the x term. If we take that negative 1 and cut it in half, we get negative 1/2. And if we take that negative 1/2 and square it, we get positive 1/4, the number that goes in this spot. Now that we've figured out the number in this spot, we can fill in the last blank. This blank is always just half of the number you see here. This number is a negative 1. Half of that is negative 1/2. So I'd get x minus 1/2 over on the left side of the equation. At this point, you probably don't see the connection between these little puzzles that we've been figuring out and this process of changing this form into this form. But we finally have all the machinery necessary to do exactly that. Let me show you some examples. Suppose you start out with y equals x squared plus 6x plus 2, and you wanted to rewrite the right side of this equation so it looked more like the left side of one of these equations up here. Well, how could you do it? Maybe first you'd subtract 2 from both sides of the equation to get y minus 2 equals x squared plus 6x. I know at this point you don't really see why you're subtracting 2, but even if you don't see why you're doing it, you could at least do it, subtract 2 from both sides to get the x squared and the x term kind of next to each other, loosely speaking. The idea now is to rewrite x squared plus 6x as a perfect square. The problem is that x squared plus 6x is not a perfect square. However, there is some number that we can add to x squared plus 6x to make it a perfect square. What I'm saying is we currently have x squared plus 6x on one side of the equation. It's not a perfect square, so we can't write it as x plus or minus something squared. However, there is some number that we can add to this side of the equation that will allow us to rewrite it as a perfect square. From the x squared plus 6x over on the right side of this equation, we kind of produce this puzzle that you see up here in blue. These puzzles you got really good at in the previous stage. Remember, our goal was to first figure out the number over on this side of the equation. Half of this 6 is 3, and 3 squared is 9. If we had x squared plus 6x plus 9, we would have a perfect square, and we'd be able to rewrite it as you see on the left side of the equation. But we don't have x squared plus 6x plus 9. We have x squared plus 6x. Solution? Add 9 to both sides of the equation. Instead of y minus 2 equals x squared plus 6x, I could say y minus 2 plus 9 equals x squared plus 6x plus 9. We're completely ignoring the left side of the equation for now and really just focusing on the right side of the equation. Note that the right side of the equation here is the exact same as the right side of the equation here. Using what we learned about puzzles up above, we know that the right side of the equation here, x squared plus 6x plus 9, is the same as x plus 3 squared. This 3 being half of this 6. If x squared plus 6x plus 9 is the same as x plus 3 squared, I can change this x squared plus 6x plus 9 into x plus 3 squared. Again, I'm completely ignoring the left side of the equation for now. All my work is over on the right side of the equation, where I started out with x squared plus 6x, recognized I did not have a perfect square, so I added 9 to both sides of the equation to create a perfect square, and now that I have this perfect square, I rewrite it as a perfect square. But the machinery in doing all of this was really just filling in this puzzle that we did up above. We're not quite done because our end goal is to solve for y here, but now that's fairly easy. Negative 2 plus 9 is positive 7, so I have y plus 7 equals x plus 3 squared. So if I wanted to get the y all by itself and have the right side written with a perfect square, all I'd have to do is subtract 7 from both sides, and I'd get y equals x plus 3 squared minus 7. It's a pretty complicated algebraic process to change y equals x squared plus 6x plus 2 into y equals x plus 3 squared minus 7. However, if you can go through and do all these steps, we go from something that we do not currently know how to graph into something that is written with a bunch of transformations that we know how to apply. We've gone from something that's ungraphable with our tools into something that's fairly easily graphable as long as we understand function transformations. This is hard algebraically, so let's do it several more times where I focus less about why you're doing what you're doing and kind of just show you how to do what you're doing. You start out with y equals x squared plus or minus some number of x plus or minus some number. Your first step is to isolate the x squared and x terms. All I mean by that is get rid of this 5. Subtract it from both sides of the equation. It kind of just gets in the way. I got y minus 5 equals x squared minus 2x. This method of completing the square only works when our leading coefficient, the number out in front of the x squared, is a 1. So if that weren't a 1, we'd want to make that 1. Fortunately, in this case, it's already a 1, so there's nothing to do. But in the next example, I'll show you what to do if this were not a 1. So in this example, we can essentially skip step 2. Step 3, we're going to add some number to both sides of the equation so that we create a perfect square on the right-hand side. As we learned with our puzzles above, that number is always half of this coefficient squared. So in this case, it would be half of negative 2 squared. Half of negative 2 is negative 1. Negative 1 squared is positive 1. So it's positive 1 that we're going to add to both sides of the equation. Common mistake is to forget to add it to the left side of the equation and only add it to the right side of the equation because we're kind of just ignoring the left side for now. But in order to keep this equation in balance, you have to make sure that you do it to both sides. So be careful there. The fourth step is just to focus on the left side of the equation and rewrite it as a perfect square. Because I picked this number in red so carefully, I've created a perfect square on this side, and I know using the puzzles that I solved above, x squared minus 2x plus 1 is the same as x minus 1 squared. So I can rewrite that right-hand side as a perfect square, x minus 1 squared. We're not really doing anything with the left side, but if you want, you might as well change negative 5 plus 1 into negative 4, just to kind of clean things up over here. Your fifth and final step is just to solve for y. In this case, it's pretty easy to solve for y. Just add 4 to both sides of the equation. So my final answer is y equals x minus 1 squared plus 4. This tends to be a topic that students need a lot of repetition for. So let's do it again. If I start out with y equals x squared plus 3x plus 2, my first step would be to subtract 2 from both sides of the equation, leaving me with y minus 2 equals x squared plus 3x. I then recognize that x squared plus 3x is not a perfect square, but there is some number that I can add to both sides of the equation to make it a perfect square on the right side. That number is always half of the coefficient on the x squared. So half of 3 squared is 3 halves squared, or 9/4. So I'm going to add 9/4 to both sides of the equation. The reason I added 9/4 to both sides of the equation is that's always going to leave me with a perfect square on the right side. In this case, it's x plus 3 halves squared that the right side is equal to. So I'll rewrite that right side as that perfect square. I might as well clean up the left side while I'm here. If you view this -2 as -8/4, you might be able to change the left side into y plus 1/4, the -8/4 plus the 9/4, and that's equal to this x plus 3 halves squared. And now we're at our last step, where all we have to do is solve for y. So subtract 1/4 from both sides. Final answer is y equals x plus 3 halves squared minus 1/4. This one was a little bit harder. Really what made this one harder was the fact that my linear coefficient, the number in front of this x, was an odd number. It introduced fractions as the number that I add to both sides of the equation, and that just kind of makes life a little bit more challenging. There's no reason you can't do things with fractions, but typically I try to avoid them. So if you can follow this entire process when we're just dealing with integers, you should feel pretty good about yourself and maybe eventually work up to this one. You might be wondering if there's any way I can make these problems any harder. Well, there is, but here's how you can deal with it. What if the leading coefficient were not a 1? Maybe you remember from the first time we went through this, we talked about the leading coefficient, the number in front of the x squared, has to be equal to a 1. If you go up to these puzzles that we solved above, it was always 1x squared on the right-hand side. We didn't see any examples where it was 2x squared over there. But what about this polynomial where y equals 2x squared plus 8x plus 1? How could we complete the square here? Well, it turns out you can kind of do the same steps. Your first step would be to subtract 1 from both sides. So you'd have y minus 1 equals 2x squared plus 8x. And then before you worry about adding some number to both sides of the equation, you'd notice that because this is not a 1, we can't do our completing the square step. But what we could do is divide both sides of the equation by 2, which would turn that into a 1. I'd get x squared plus 4x on the right side of the equation if I divided each of these terms by 2. I'm not going to bother simplifying the left-hand side. I'll just leave it as y minus 1 all divided by 2, because eventually I'll be solving for this y, so there's no point in really simplifying it right now. On the right-hand side, I now have x squared plus some number of x, which is not yet a perfect square, but it's set up in such a way that there's some number I can add to both sides to make it a perfect square. In this case, that number is a positive 4. Half of this 4 is 2, and 2 squared gives me 4. So I'm going to add 4 to both sides of the equation so that I have a perfect square on the right. I'll leave the left side alone for now, kind of a mess, y minus 1 over 2 plus 4. But the right side, since I have written x squared plus 4x plus 4, I can rewrite it as a perfect square, in this case x plus 2 squared. I'm almost done here. My last step is just to solve for y. To get this y all by itself, I'd first subtract 4 from both sides of the equation. So I got y minus 1 over 2 equals x plus 2 squared minus 4. And then if my goal is to get at this y, I'd get rid of this 2 next. So I'd multiply both sides of the equation by 2. On the left, that would just leave me with y minus 1. And on the right, you got to be a little bit careful. There's 2 terms here. The x plus 2 squared is one of my terms, and the 4 is the other term, and I'm subtracting those 2 terms. I want the 2 that I multiply by to hit each of those terms. So the 2 gets multiplied by the x plus 2 squared, but the 2 also gets multiplied by this 4, making it a minus 8 over here. A common mistake is to put the 2 here and forget to have the 2 hit the 4 to make this 8. Another common mistake is students are tempted to take this 2 and distribute it into these parentheses, but you can't do that either because the stuff inside the parentheses is squared, but the 2 is not. So if you distributed the 2 inside the parentheses, you'd essentially be treating this like it were squared, when it's not. Anyways, we're just about done. Our goal was to solve for y, so now I'm going to add 1 to both sides of the equation, and my final answer would be y equals 2 times x plus 2 squared minus 7. This is about as hard as these questions can be, so if you could follow that one, that's really good, and this seems like a good spot to end the video.